So let me introduce myself. So I'm Christopher Schiller-Priest. This is Stefan Stoltz, and we have Pavel Mem. We are the organizers. So if you have a question, you can come talk to one of us. Welcome. I want to extend a warm welcome to all of you for joining us here. This is the 2024 thematic program on topology and quantum field theory. It's my pleasure to introduce our first main course instructor, Konstantin Wernli, who's coming from the University of Southern Denmark, and I can't talk this morning. His title is Locality and Globalization in Perturbative quantum.
Yeah, thank you very much, Chris. So thanks to the organizers for putting together this school and inviting me. I'm very honored to be the first speaker and glad to be back in Notre. See some familiar faces and a lot of new faces. So yeah, as Chris said, I want to talk about locality and globalization. And globalization. Then since I'm the first speaker, so maybe I'm allowing myself a little pep talk. So we're all here because we love math and we love to do research on math. And I think that one of the greatest challenges for math research, okay, in this century, or if you want to be more grand, in this millennium, is to put QFT, like quantum field theory, on a rigorous footing. So that's a challenge for all of us that we're doing research in math, and especially for the new generation of researchers like you. And I think that the main problem is to actually understand non-perturbative QFT. Okay? So you can see that non-perturbative QFT is not what I'm talking about. So, but that's because I don't think we have a good understanding of this yet, and the goal of what I'm trying to explain is to come closer to a definition. Okay, and there are some, let me just plot some words. There's some really big open problems. There things from physics that we don't mathematically understand, but that are kind of super important. I would mention non-finite, so if you don't know what that is, it's like in the universe there are four forces, and one of them is a strong force that holds atoms together, it holds protons together. And I think the perturbative understanding of QFT doesn't really explain why the protons are actually stable. They're just make up all the mass around us, right? And why is this mass here? Is it really stable? Yes, but it's okay, our model doesn't explain it. There's another more famous problem called the mass gap problem, which maybe you might know because it's one of the millennium problems of the Day Foundation, and if you solve it, you get $1 million. And finally, there's also quantum gravity. So we very well know that we don't have a theory of quantum gravity, and that for understanding the universe we do that. Okay, so those are problems coming from physics, but for which there's both in physics and math we don't have a good understanding of them, and it's kind of a motivation that's driving mathematical research in quantum field theory. Okay, and so now we should forget all of these things again, because I'm not going to say anything about those anymore, but I just want to sort of this whole explaining that I think it's important that we study quantum field theory in mathematics, and that I think many exciting development in mathematics have come from this in the last years, and I'm sure many more have to come. So I want to talk about comparing two particular mathematical formulations of quantum field theory. So two formulations, QFT, two mathematical formulations of QFT. So there are many, of course, and yeah, I'll just focus on two of them. So let's start by recalling integral. So in my model for field theory, I have a space-time M, which is the manifold, and then the space of fields attached to it. And then an actual function on the space of fields, for instance, in electromagnetism. Space of fields is just a space of one forms, and the actual function. You just need you take the differential of your one form and touch star.
Sorry, I think there's a typo. It should be R4.
It should be M here. Sorry.
Okay.
I meant value is R
Uh,
instead of some other real world coefficients. Thank you. And then, okay. You could write down this supposed type integral. So let me write down the integral coefficient function. So we want to just integrate exponential action over the space of fields. And that's one of the path integrals appearing in Feynman's formulation of quantum field theory. So this is not mathematically defined in most cases of interest. Right. And there are two formulations of this integral that axiomatize different properties that we would expect. Okay? So this isn't a mathematical definition. Scale quotes here. And now, so from this, there are two mathematical definitions that are derived from this hypothetical integral. So one is what I would call vectorial field theory. So usually we attribute that to T and Siegel around 90 for TQFTs. Right, so here you make a definition that the partition function is that functor in the simplest formulation is the functor from coordinates category to the category of factors. And of course, by now this comes in many different flavors. So let me also mention the Stolz-Steiner formulation for Riemann. So Riemann factorial QFTs. I think that was around 2012. Yeah. So here you would say, okay, whatever this path integral is, it gives a functor from a coordinacy category, and what you're doing is you're axiomatizing the Fubini property of the integral. Okay, so if you think that your integral satisfies Fubini and you're using locality to QFT, then you can arrive at this definition. And there's another definition that uses that's closer to physics. So, I mean, in some sense, you can say also due to Feynman, and that holds in the sort of asymptotic regime H bar goes to 0. So, if you look at the form of this integral, you can see that if h bar is very small, which is, I mean, in main nature is very small, right? Then this integral is really oscillating wildly, and most of the contributions to this integral are killed, except the one that are very, very close to the stationary points of the phase. So there's something called stationary phase approximation. Here, and this is what results in the same diagrams you can see if you that's the physics way of making sense of contribution. And so here you would say that there's another kind of gadget which you can define, and it's some three factors times some divergent formal power series, coefficients, A and oh, we have two, and this is the one I'm going to be talking a lot about later in this course. So I'll explain how to define this. And so now that we have two, we have two completely different axiommatizations of one and the same path integrals, right? And of course, the question is like, what is the connection?
Konstantin, have you had an annoying audience member?
Yes.
A lot. There's definitely some kind of axioms, but on the right, it feels like you just wrote down a power series.
Yeah.
It sounds to me there's that kind of axiomatization, or excuse me, there's like a process on the right.
Yeah, there's definitely an algorithm going from the pair FM and FM to this guy.
So the algorithm will be there in the definition of the
And then there are some axioms that this guy satisfies. So in the formulation I'm using. And so actually it's a good question because okay, now I want to talk about like why is it okay, there should be a connection, of course. There are two ways to make sense of the same integral, but why is it interesting to study? So so on my notes I'm going to like down here, but I can't really. So this board
Also
doesn't
to
go
make
up,
a
right?
remark, that board does not move, so it's best not to use the dashboard
Yeah.
to pull up the other ones.
Okay, I guess I learned it the hard way now. So I'm just going to write the pure name. So these kind of the functorial field theories, they're inherently non-competitive. And they sort of incorporate the physical principle of locality. So kind of what we would hope to do is that we would want to get some pair like that, and then give us some function. Ideally. Okay, because really if you want to have a, sorry?
I'm sure you got it cut off.
Oh, yeah. Yes, I'm learning the board management here. So we can put things in a big perspective. Okay, we're interested in understanding non-perturbative quantum field theory. One mathematical formulation of non-perturbative QFT are these functors. But there isn't really a direct way to go from classical field theory to a functor of that form. Okay, and but there is a, as Owen said, so there is like an algorithmic way to construct this perturbative quantum field theories. So, kind of in a big overall scheme of things, I hope that like we will, by understanding this connection, we'll come up with a way of constructing these functors more directly from the classical field theory that's given by a space of fields and its action function. And so some examples. So I think that the most prominent example for me is that here you have the WRT PQFT. So with the speaking graph, right, maybe once. Right. So well, this is, and I think by now it's sort of commonly agreed that this is a functor that corresponds to what we call Chern-Simons theory. Chern-Simons. And we describe Chern-Simons path integral here, and you will see like what it means later if you don't know yet. So yeah, I would say the status is still that it's mostly a conjecture, but it's sort of commonly agreed that it's true. On the other hand, you can construct the perturbative Chern-Simons invariance relatively directly. This was done in the 90s by many people. And just write a few names of use. So one construction is the Konstantin and Kugelberg first in school. And then there was one to Axelrod finger, and then those are two different ways to actually define, make sense of the perturbative and Simons invariance, which is why this is separately. So there was another line where a couple of people worked on this. Was Axelrod and Singer wrote two papers, and then Brabot and Roberto Catania wrote two papers, and then Catania and Pablo wrote another paper about this. And finally, there's also the what's called Lim Wakami Utsuki invariance. And so here there's a purely mathematical question of here we have a invariance of three manifolds that are coming from a nice extended PQFT. Here we have some universal finite type invariants. Okay, so what is these guys here? This depends on the parameter k, right? And so as k goes to infinity, you would expect, it doesn't make this a full arrow. You would expect that you get those kind of perturbative invariants from the but yeah, this problem has been sort of known ever since these people wrote these papers, and this is around 91.
H0.
Yeah, sorry, this is K, right?
Ah, sorry.
Which means 8 part is it. And yeah, and this was, they didn't even write more people. There was also Byron found in 92 and physicists before that, but it was around the same period, right? So early 90s. So over 30 years, we have known this problem, but yeah, it's still okay. So a lot of people have worked on it. There are some partial results, but yeah, by and large, that conjectures.
Sorry, can I ask? So as you said, like it's
I don't know, believe that there is this equivalence between sticking drive and silence.
Yes.
But now you're saying, what about the other one? But in which framework are you checking an equivalent?
So there's like there's a very concrete question. So if you want like this thing is a number, or it's a sequence of numbers depending on k, and there it has some asymptotics as k goes to infinity, and you want to, I mean, the conjecture is that both asymptotics coincide with this gadget here, if it's defined correctly, okay, but
Okay, so it's only about the invariant.
I mean, that's one formulation. But there's another thing you could add, so you could take the PQFT. It also depends on some level k, right? So you could try to see what happens when you take k to infinity there. It's actually not fully understood what is kind of the limit, like the asymptotics of a TQFT. And then you can try to compare that to what I was going to say next, namely that now so like one plan to attack this conjecture that hopefully helps us to understand this more general picture, and then finally maybe have some ideas about both questions, is to kind of enable the cutting and gluing of the perturbative point field theory. Okay, so that's what I'm going to talk about in this series. And yeah, I think sort of as an answer to your question, I see that in my notes I actually have another diagram I wanted to draw. So final diagram before we start doing some actual math, maybe. But let's write again. Physical. So now I said, okay, so on the one side, we have the functors, we have the perturbative PQFT, so we don't know what's the connection. And now sort of, and the idea is to put another level to this diagram. Okay, so we first study asymptotics of this as a functor, and then we'll maybe give us well, we don't know what this is going to be, but it will be something that describes the asymptotic of the asymptotics of the PQFT. So here we'll kind of enable cutting and gluing of those perturbative guys. It will give us another version of the perturbative partition function that, okay, so as a slogan, I'm going to write this functor, but it's not going to be a functor. And then, like the hope is that it will be simpler to compare those sketches, okay? Because now you have two things that actually they are compatible with cutting and gluing. And then once we have that, we can compare that on building blocks, maybe. So depending on how far we can extend, like there's only a number of generators. I think that's something that Chris knows very well. So finite number of generators that we have to study. So maybe this will help us in kind of attacking these things. Okay. So concretely for solving this conjecture about WRT and perturbative consignments, but also in other field theories, it's trying to extract functors from the perturbative formulation. So now the plan for the rest of this class. Okay, so one, I'm going to say a few more things about classical and quantum theory, not so much, but a bit. And I'll talk about perturbative compensation. So this is this algorithm to construct the perturbative function. And I will use this tool called the formalism. And I talk about copying and doing of those things. And then hopefully about globalization. For globalization, that's about some mostly work in progress about extending the perturbative partition functions, which are otherwise defined only at sort of one reference point in the Euler-Lagrange space, extend them to hopefully differential forms on the moduli space of Euler-Lagrange solutions or moduli space of factors. So hopefully there would be some sort of, I mean, ideally in the end there's going to be some top form here that you can integrate in the rush here, but we're still a long way away. We are still quite a bit away from that. So, yeah, any more questions before I start talking a bit more serious things and less hopes and dreams? Yeah.
So do you think you'll get everything in the bottom left in this process, or you just kind of give a collection of examples? It's not clear that everything, like you keep trying zeros to go back and forth, but it's not clear to me that you expect them to go both ways.
Yeah, I mean, this is very significant. So, how far we can push it and in what examples it's a bit up for grabs. But I don't know. I mean, in the end, the methods are pretty general, and you know, so it's kind of clear how to, if you have a pair of an space of fields and action functional, it's kind of clear how to construct a perturbative quantization. I think even if you have to renormalize, you understand.
All of the factorial things is coming from Lagrangian field theories.
Sorry?
You don't think of all that factorial things as necessarily coming from Lagrangian field theory, right?
Oh, you're saying that there might be some functors that.
In the bottom left.
Yeah, no, I mean, I'm not claiming to get all of them. Yeah, no. No, I'm saying that let's start with the, but let's start with the Lagrangian field theory. What's the associated functor, right? So, I mean, many examples you can know. We don't even know if there is one. If there is one, what kind of. I mean, functor is very restrictive. Like, could be some more like relaxed gadgets. And so, yeah, so I'm trying to sort of get to this bottom left, and then in some cases there's also like a way to go back. Okay, you have some asymptotic series for something, and sometimes you can find the gadget back again, sometimes you can. There's nothing is very simple, but it's a plan, right? Sketch. Okay. So, so I'll start with the first part and let's start any other questions. Let's try to do this back now. Okay. So let's start with the definition of what I think is the classical field theory. One possible definition. So classical field theory and manipulate M. So some fiber bundle over M. F over M. And then a function and that Sm from sections of the fire bundle. And I will note this section, the space of sections by F. And then we don't, so we usually require F to be local, and then it's, let's say this one's, well, it's one possible way of formulating this, so let's say F, so the action function, it's local if S is the integral of the dimension, and here the Lagrangian is a function, the bundle map from the that bundle to densities. Okay. Here this is the case for the that bundle. Bundle map. Bundle. Hey. A is called order of this. Okay, and so here case that bundle, it means that you can take all the sections and their derivatives and evaluate them at points. Okay, so this Lagrangian is a density and its value at some point x depends on the L of sigma evaluated at some point x. It just depends on the value of that section x and the first k derivatives.
I think this is contrary to the standard terminology where something like scalar fields, you know, P dots would be called like the P would be called the second order theory. So it depends on the first guess.
Right. And
But sorry.
yeah, that's it. It's not important. But so for most examples, actually for all the examples we will consider in this course, so F is just a vector bundle. Okay. To make some things easier, we represent the space of fields as a vector space. Okay. There was this for it, and this for it. There's this one.
If the words about where is from local, where is subjective here?
Sorry?
What's local about the action here?
Yeah, so that's just one way of saying that you can recover this action sort of from smaller pieces of M and putting it back together.
It's not the same local that is for unity GFTs, right?
I think it's the same local, but
It's the same
not really
mathematical.
sure what local that is.
And the non-local thing would be, well, you look at the value of the field, say it's a scalar field, look at the value of the function at one point, compare it with the value of another point, look at the difference, and you say, oh, that difference sort of matters. That would be sort of like sort of action at a distance, sort of you need to immediately know what the value is here, what the value is there. That should be forbidden. So this local says, no. You just look at locally if what happens with the value of the function and its derivatives, and then you can sort of average that by taking the integral over M But in that sense, it's local. No sort of, you're not comparing the values at or derivatives of your fields at different points in your space time.
But maybe the confusion is like Euclidean versus Lorentzian.
No,
It's Euclidean, right?
there's not necessarily metric. Yeah.
Okay,
Oh, this doesn't depend on Euclidean.
okay.
Okay.
Sorry, how can we include the example of connections? The space of connection,
Well, connections are sections of a fiber bundle.
what fiber bundle?
Good question.
It's a word for a nice fiber bond, right?
Yeah, yes. That good sections are connections.
I don't know.
If it were a trivial bundle, then it would just be,
Yeah, trivial bundle is.
and it's sort of like, yeah, it's a twist of that, so it's not quite a
Yeah,
active bundle, but it's a torso over one, so yeah, close enough. So in other words, the difference between two connections on the same bundle, that can be interpreted as a section of a vector bundles.
but I'm asking the general, yeah.
No, it's a
So
good
that is
question, and you taught me, I don't remember how to define it. I know that there is a fiber bundle in sections of connections. And usually, yeah, we only work with trivial principal bundles where the
Yeah.
connections are just differential forms.
Yes.
Well, so this doesn't include connections and also Putman models, right, where you decide on the interest in the bank, that with another name. So yeah, I'll discuss some examples in a second, but first, let me define this Euler Lagrange space. So now, we don't say M has to be closed, but let's just say for now M is closed. And then I can define the Euler Lagrange space as all those fields are the variational derivatives of the action vanishes. And one way to say that is that if you take derivative with respect to epsilon or the action I just epsilon v, and that is 0 for all the f. And right, and of course, this makes sense only if the space of fields is a vector space, but if the space of fields was a manifold, we would replace it. We would replace this with the flow of the vector fields. Just really fine. All this variation derivative of m apply to the. Okay. Okay, so now examples. Well, maybe let me say first that somehow so for classical physics, of course, I'm totally oversimplifying, but somehow this space is the only thing that's important. So if you have some observable so the observable is something that we want to know the value of. So we have some function. We want to know the value observable. Oh, that's just some function on the page here. Then, so if, and that's a big if, but okay, if the one we run locals is a point. So classical physics just predicts that at the value of O, of this 5 zeros. Any physicists that want to strangle me now? Looks good. Okay.
Sorry, is there something that distinguishes observables from actions?
No, the action isn't observable itself. Yeah.
But there are observables that aren't actions.
Yes, yeah. Okay, I mean, yeah, now we're getting to the subtlety. So I said that, okay, actions has to be local, right? There are local observables, there are non-local observables. Then depending on the kind of field theory, yeah, we will have to restrict the classes of functions that actually are observables. So for instance, I just said that something, this is a space. I said, okay, if this space is actually a point, then okay, you can think of all functions as observables. If this space is not a point, yeah, then it's more complicated.
I'm having a question about the terminology. So in my thinking, classical observables are functions on the space of classical solutions. So it would be a function just on this one point when you have just one classical solution. Whereas here you're saying a classical observable should be a function on the space of all fields. Well, classically, all fields are not possible. Only the classical fields, the solutions of the Lagrange are possible. So I'm just wondering, I mean, I'm a mathematician, so I have no idea of how you guys talk about these things. Sort of, what is the convention here?
Well, I would say that observable is a function in space of fields, right? For instance, if you have an electromagnetic potential, so it's in one form, Y4, and you can have some charge. And that charge is defined for all potentials.
I see.
And the one that, yeah, we all have something to say as well.
Space of solutions is a subspace of the space of all functions. So functions on the space of solutions is a quotient algebra of functions on all fields. So, I mean, that would mean that if you're thinking about them as evaluating on solutions, then of course there's representatives that are functions on all fields. But you might want to assume that it's get the same answer. I don't know what you think of as the.
Yeah. So you're saying no, sort of like thinking of functions on the whole fields, space of fields is sort of, you call that classical function.
I mean, I think that's, yeah, we have to ask what they're.
Okay.
So can I also say something? So I think that oftentimes when you talk about observables, you talk about local observables, like in quantum, like in classical mechanics, like position of a particle as time t0. That's an observable. And then you can of course ask what's its value on some classical solution. So so this Euler-Lagrange locus is something non-local, less an observable is a you usually specify it as
Local thing.
yeah, as a local thing.
Okay, great. Thanks.
Well, it was a very innocent remark. I didn't want to have a unique discussion about this. Maybe.
Sorry.
Maybe we should. I don't know. I don't know. It should happen. Okay, but let's look at some examples. Example. So and it's one of the simplest field theories is the scalar field theory. So here the fiber bundle is this function R or space of fields. It's functions and action function is 1/2. That's phi is 1/2 d phi star d phi. And then there's some parameter that you could call mass, m squared phi. Okay. And the Euler-Lagrange locus. So that's the solutions to this Helmholtz equation. That's n plus pi squared equals 0. So if I remain manifold, okay, then I have a hot star, right, on this manifold. I also have a sometimes called the granular Laplacian functions. So this Laplacian is plus or minus v star.
So the star stands for like, yeah, take the thing and wedge it with star of itself.
Yes. I have this bad habit of not writing wedge symbols. Yeah. So, and okay, I mean, typically you would say m squared is a mass and it should be positive, but it could be 0. And if it's positive, and I'm using the convention where this has a positive spectrum, so then the solution should just be trivial, 0. But if you m squared could also be negative, and then or 0, and then this might have, if it's just an eigenvalue of this Laplacian, then there's a very non-trivial space of solutions. So another example. Primary theory. So you pick some, here you have a three-dimensional manifold. No remaining structure will fix some quadratic Lie algebra. And yeah, now the space of fields is just,
You remind me what it could radically algebra.
yeah, it's just a Lie algebra with invariant in a pairing. Invariant pairing.
Sorry, what is the symbol you used to that?
Sorry? Math like G. Kind of. Yeah. Spatial fields is Lie algebra value in one form. And then those will be followed up as connections and trivial principal number. And so under some restrictions on the Lie algebra, on the Lie group, principal bundles in 3 dimensions are always trivial. So not really that big of a restriction. In that case, you can write the actual functional this 1/2 a and bracket with the a. So here you take wedge product of the forms and you take bracket and then the algebra. So G has this invariant pairing. So now there's a small exercise, or great exercise if you've never done this before. It's to check that the order of locals is given by flat connections. Which is no space that satisfy the equation of dA plus somehow a bracket with itself is 0. And the second part of the exercise is that this space is invariant under gauge transformations. So if A is flat, and so A G, so this is G will be inverse plus G minus 1 dV, where G is a map from M to G, and this is the simply connected Lie group integrating G. And I think in order for this notation to be meaningful, I'd rather assume that it's a matrix group actually. mean, of course, it is true if this group is not a matrix exclusion. Right, it needs simple notation. Assume that. So we can see that yeah, so here we're already in a situation where the Lagrange locus is actually quite complicated, and it also has a large set of symmetries, meaning that it's extremely not a point. Okay, so it's actually very, very big. And the quotient, well, let me call this, let's call this omega 1 flat. And very good notation. Divided by H symmetries. So the quotient is called the moduli of flat connections. Flat connections, and we have a purely topological description. So that's also called representation variety, because yeah, it's just homomorphism from the fundamental group in the D. Character variety. You know.
Ask you an annoying question.
Yes.
Choose to ignore it. Or which one? So, when you say quotient, thinking about like a quotient topological space, a quotient stack. They're sometimes bad.
No, I mean here for now is I can just think about it as a topological quotient, for instance.
So it's not necessary.
Yeah. I mean, you can say many things about this quotient and its isomorphism, and from now on up with that. I'm just saying that so yeah, so the physics field theory, this Wernli theory, it kind of knows about this purely topological gadget fields. So it's kind of interesting. All right. Yeah, let me just maybe one or two more, because I like examples. So electromagnetism. So here, space of fields is just one force, and I think we had it on the board before. So action functional, okay, without sources, this is a bit boring, but it's just dA star dA, and then all the Lagrange locus is just solution of Maxwell equations, so dA and C star dA is equal to 0. The solution is Maxwell equations in vacuum, right?
So have we assumed have a compact?
It's dangerous if it's not compact.
No. If it is non-compact, I think the polar equation is just harmonic.
Sorry? No, if it's not compact, I should assume some maybe follow-up conditions to leave this integral conversion, right? Compact
I think the polar Lagrange equation is different in non-compact.
Is it though?
Because the harmonic form are not the forms satisfy those three.
So let me just assume that it's compact for now.
So I don't think that those are the correct sort of Lagrange equations. The equations is d star dA equals 0. Only one equation, not two equations.
D star.
Yeah, D star dA equals 0.
He started that curvature, right, not of the connection.
Yes, the star of the curvature ranges, yes.
Okay, and this is the greens.
But I think that if I'm in compact, those two are, we can use those two equations.
So
Does this mean that A is harmonic and then dA is closed, right?
Yeah.
yes, like on a compact manifold, yes. So one should be to compact manifold really. Yes.
And
I think usually one can take a non-compact manifold, but one should ask for the equations of fields to be compactly supported.
yes, yes. But that would be the same equations, no?
That would be the equation D star dA equals 0.
Yeah.
But you couldn't use Hodge. Maybe that.
Okay, and I'm assuming that means. Yeah, of course, I kind of, for simplicity, always work with this assumption, and I'm lying to myself that nothing really changes and just goes a line. So I keep being more careful and stop it. And finally, I think we can time for one more example and then break. And sorry for the rest this afternoon. So yeah, the Gamma-Mills theories of spatial fields. Yeah. Again, we have some structural algebra coefficients. So I'm assuming there's some trivial principal bundle over my manifold and action function. Fa is our Fa, and Young-Mills equations are EA star A equals to 0. Sometimes what I call sometimes assuming that M is complex, so let me just make that function implicit. Okay, but I think maybe we'll have a break now because it's almost over and then we can continue the talking.
Questions? Few questions during the talk. So, okay, we'll break now. There's coffee back in the room we were in this morning, and we will resume at 11. Be back here.
We leave our stuff here.
Leave this stuff here.
I mean, generally speaking, it's pretty safe. So I think that would be fine, but if you want to be on the safe side, you take it along, so that be up to you. First.
Sorry. I think, yeah, we should somehow allow